All right, as we continue journeying through reactions, we're going to talk about two types of acid-base reactions, and the first of those is a neutralization reaction. Okay, this is going to require us to pay attention to the patterns. Okay, there's a lot of patterns in these that always do the same thing every time the things are reacting together. So if we can pay attention to those patterns, we'll be able to figure stuff out as we go. Okay. Our neutralization pattern tells us that an acid plus a base is going to react and give us water and a salt. Okay. Salt here is being used as a general term, right? It could mean sodium chloride if we have sodiums and chlorides in there, right? Because sodium chloride is table salt. That's where we get the word salt from. Well, backwards. That's what we think of when we think of salt. But really, salt is any ionic compound. Technically, it's the ionic compound that's a product of the neutralization reaction, okay? But the salt is just any ionic compound, okay? If we have a hydroxide base, then we're gonna get water. I think that's my next little pop-up, dude, yes. Okay, and a hydroxide base is gonna give us water. Okay, so the way I think of this is we're gonna take an acid, react it with a base that has hydroxide. We're gonna get water, and the crap that's left over. The salt is always the crap left over. Okay, and so we can figure this out using a metathesis. And we talked about this with precipitation reactions, right? You can think of your acid is really two things, right? You have your H and you have whatever the other rest of the acid is. Your base is whatever the base is, plus probably hydroxide. Okay, this is going to give you the salt, which is the crap that's left over, which is the B and the A. And then the water is going to be H and OH. So you can think of this as a metathesis. This will also help us balance things. Remember, we talked about saying if we think about water as HOH, it'll help us to balance things as we go. Okay, so let's start diving in here and looking at what some of these patterns are and try to predict some stuff as we go. All right, so let's predict this. We're going to take HBr, which is a strong acid, and calcium hydroxide, with a strong base, and we're going to predict the products. Okay, our products should be, do we have hydroxide? Yes, so we're going to get water, and that water is liquid. Okay, we're gonna get a salt that's the crap that's left over. So that's Br minus and Ca2 plus. So let's make a formula of those two things. Shit, go back. Formula that's those two things together, which would be CaBr2. And if we look at our solubility guidelines, calcium bromide should be soluble. Okay, ultimately then it's on us to write and balance a complete equation here. So HBr aqueous plus calcium hydroxide aqueous should give us water, liquid, and calcium bromide that is aqueous. Okay, now I want to balance it. We need two BRs. Okay, that gives us two H's and two OH's, so we need two waters. Okay, there's our balanced molecular equation. My next task for us is to take this balanced molecular equation and come up with the net ionic equation. Okay, with a neutralization, it's going to be best if we just do it the long way that we learned, right? Break apart all of our strong electrolytes and then cancel out the spectators and then write the net ionic equation. Okay, so 2HBr means we're going to have 2H plus, right? This is a strong acid, so it will dissociate. We're going to get 2Br minus as well. We said calcium hydroxide is a strong base, so we're going to get a calcium 2 plus. Then we're going to get 2OH minus aqueous. Water is a non-electrolyte, right? This is liquid, 2 water, liquid, so it stays together. Calcium bromide is ionic and aqueous, so it comes apart. Ca2 plus, oops, aqueous. And 2 Br minus, aqueous. All right. With our complete ionic equation, we can cancel out spectators. There's going to be fewer than we like, right? Calcium 2 plus cancels out. Bromide cancels out. Maybe not. Okay. And now we have our equation. 2H plus aqueous plus 2OH minus aqueous gives us 2 water aqueous. All right. A lot of us might stop here. Okay. But I want us to remember our balanced equations have the lowest whole numbers possible. So what that means is we got to get rid of these 2's. 2, 2, 2. I mean, if you're actually doing this, you can just erase the 2's. I'm going to rewrite it just so we have it all there for our notes. H plus OH minus makes water liquid. Okay. Now, the nice thing is, if you look back, and we did this at the beginning of this, right? We went over here and we said, look, we have a strong acid and a strong base, and we predicted our stuff. Okay. If you know you have a strong acid and a strong base, then this is always going to be your net ionic equation. Shoot, go back. Always, I can't spell. Always for strong plus strong. Okay. If it's not a strong acid plus a strong base, this is not your net ionic equation. Do not look at a neutralization reaction and write that H plus OH minus makes water, because you're going to be wrong sometimes. Okay. I want you to be right more often than you're wrong. So only for strongs do you want to do that. If you want to forget I said it and just do it the long way, do it the long way, because you're going to get it right that way. All right, let's see what happens when we don't have a strong. In this case, we're going to take a weak acid with a strong base. Let's react hydrofluoric acid and potassium hydroxide. We're going to predict the products and write the net. Okay, so hydrofluoric acid is HF, aqueous. Potassium hydroxide is KOH, aqueous. Okay, again, we can do this with the metathesis. We can also do this knowing our pattern. We have a hydroxide base and an acid, so we know we're going to get water that's a liquid. Okay, and we're also going to get the salt of the crap that's left over, which is K and F, so we should get KF aqueous. Okay, look at it for a moment and convince yourself that this is balanced, and yes, it is balanced. Okay, now we're going to write the net ionic equation, and what I want us to remember as we start this, HF is weak. And if it's weak, it's not going to dissociate for the net ionic equation. Even though we wrote aqueous, this is still HF together. Okay. Potassium hydroxide is strong though, so we can get a K plus and an OH minus. This will give us a water that doesn't break apart because it's liquid, and we'll get a K plus aqueous and an F minus aqueous because KF is a strong electrolyte. All right, what are our spectators? Look at it, maybe pause, think about it. Okay, do we see it's just potassium and everything else is the same? So our net here should be HF aqueous plus OH minus aqueous gives us water liquid and F minus aqueous. When we're done with this, our net ionic equation should still be balanced, right? We still have one H, one F, two H's, and O, right? Our charges are balanced. There's one minus on each side, so this is okay. All right. All right, let's flip this over and do a strong acid plus a weak base. Okay, this is going to look a little weirder, but we can still do it. Okay, we want to take chloric acid and pyridine, and we're going to react them together, and we're going to predict the products, and we're going to write the net ionic equation. Okay, so let's take a stab at this. All right, let's say chloric acid, HClO3, aqueous, plus pyridine, C5H5N. I gave us that over here. You don't have to know pyridine. Aqueous. This is a weak base. All right. We cannot do the metathesis because there's not OH minus. And if there's no OH minus, there's no water. Okay. So I'm going to even write that down. No OH minus means no water. Okay. So what happens then when we do this? Well, the two things react with each other and make a new ionic compound. I know this is going to be crazy. Okay. That's essentially the two things smushed together. C5H5NH, ClO3, aqueous. You're like, what? Okay. That's what happens. The two things get smushed together. This is where it gets a little bit wacky and weird. We don't have water, so there's no hydroxide. All right. What does the net ionic equation for this look like? It looks a little weird, right? This thing that we just wrote, let me switch colors here, is really two ions together, C5H5NH plus and ClO3 minus. Okay, this is an ionic compound that has a weird cation. Okay, so when we write our net ionic equation, we can say, okay, well, let's break these down. Chloric acid is strong. We said that in the beginning. So H plus aqueous plus ClO3 minus aqueous. Pyridine is a weak base, so it's going to stay together. C5H5N aqueous. This gives us, and we said what these break into, C5H5NH plus aqueous and ClO3. That looks garbagey. ClO3 minus aqueous. Okay. Then the process is now the same. Look for the spectators. Chlorate is their only spectator. So the net is the rest of it. H plus pyridine makes C5H5NH plus AQ. This pattern will feel similar depending no matter what the weak base is. Your products are going to look a little bit weirder because you don't have hydroxide, but this is how it works. Okay. If you need anything, let me know. I'm here. Ask questions. I'll see you in class. Have a good one.